Hello everyone and welcome to our series of video lectures on unsupervised learning and algorithms under unsupervised learning. My name is Priscilla Chamenyi. I am a junior data scientist for global communities in the Laboratory of Data Science at Purdue University, Fort Wayne. In the last video, we looked at affinity propagation. In this video, we are going to be looking at singular value decomposition, SVD. So let's jump right in. SVD is a powerful mathematical tool that provides a factorization of a given matrix into three matrices. Now, these matrices are a unitary matrix, a diagonal matrix, and its conjugate transpose. In machine learning, SVD is often used for dimensionality reduction, data compression, and denoising. Its goal is to reduce the number of dimensions in the dataset while preserving as much information as possible. Now we're going to look at how SVD works. So first of all, SVD identifies the orthogonal axes that best capture data variation. These axes are called singular vectors, and they correspond to the principal components of the data. Now, the singular values in the diagonal matrix are the magnitude of these components. These components represent the most significant directions of variance. By selecting only the top k singular values in vectors, the dimensionality of the data can be reduced to k dimensions. The algorithm, or SVD, is denoted by the formula A equals US V transpose, where U and V are orthogonal matrices. This is where algebra comes in. S is a diagonal matrix, and S values are considered singular values of a matrix A. Now, the SVD of an M by N matrix A is given by the formula A equals USV transpose, as already said, where U is our M by N matrix of the orthonormal eigenvectors of AA transpose. V transpose is the transpose of an N by N matrix containing the orthonormal eigenvectors of A transpose A. And lastly, S is our diagonal matrix with R elements equal to the root of the positive eigenvalues of AA transpose or A transpose A. This is an example code of applying SVD on a dataset in R. As usual, our dataset is the IRIS dataset, 150 data points, the 4 numerical features, and our 1 categorical feature. So the IRIS data is applied on SVD is applied on the IRIS data to reduce the dimension, and then we have the plot below. The outcome of the plot is, we can see that the outcome of the plot is this. We have 3 clustering groups based on principal component 1 and principal component 2. If you have been following the videos, we spoke about something, we talked about principal components when we looked at PCAs. So this is the output. We see that we have 3 species: Setosa, Veriscala, and Virginica. So based on these 2 principal components, SVD has been able to classify or cluster the data points into 3 species. That's what the output is saying. Some advantages of SVD is that it can reduce the number of dimensions in high dimensional data, making it easier to visualize and analyze. It also has various applications in fields like image processing, NLP, and recommendation systems. Lastly, the singular values and singular vectors obtained from SVD can provide insights into the structure of the data and the relationship between features. On the downside, SVD assumes that the relationships between features are linear, which can limit its ability to capture complex nonlinear relationships. And it is also sensitive to the scale of the features. This brings us to the end of today's lecture video. Today's video is going to be the last video on this series. That does not mean that all the series we've done so far are the only algorithms under unsupervised learning. There are many more algorithms under unsupervised learning, but this is just how far we'll be able to go for now. This work is brought to you by the Laboratory of Data Science and the Indiana Data Mine Grant, and it is supervised by Professor Alessandro Selvitella. Till we meet again, bye and thank you.